March 1943, and the Atlantic Ocean was becoming a graveyard. German U-boats were hunting Allied convoys with terrifying efficiency, sending merchant ships to the bottom faster than shipyards could replace them. In February alone, 63 Allied ships had been sunk, totaling over 350,000 tons of desperately needed supplies. Food, fuel, ammunition, aircraft, tanks, everything Britain needed to survive and fight was being torpedoed into the cold North Atlantic depths. The numbers told a story that kept Winston Churchill awake at night. Britain was an island nation that imported 70% of its food and nearly all of its oil. Cut those supply lines and the war was over, not lost in some dramatic final battle, but strangled slowly as the nation ran out of everything. Fuel rationing was already severe. Food rations were being cut monthly, and the projections showed that at current loss rates, Britain would be forced to negotiate surrender by the end of 1943. The U-boat wolf packs were winning. Admiral Karl Dönitz, commander of Germany's submarine force, had refined his tactics into a science. His boats hunted in coordinated groups, striking convoys at night when escorts were blind and helpless. A single convoy could lose a dozen ships in one night, 60,000 tons of cargo sent to the bottom, along with hundreds of merchant sailors who died in freezing water or burning oil. The Royal Navy was doing everything possible to fight back. Destroyers, corvettes, and frigates escorted every convoy. Aircraft patrolled when convoys were within range of land bases. Depth charges, sonar, radar, every tool available was being thrown at the U-boat threat. And it wasn't enough. The Atlantic was too big, the convoys too slow, and the escorts too few. But in a small workshop in Letchworth Garden City, about 35 miles north of London, a man named Charles Parsons had an idea that seemed absolutely insane. Not the famous steam turbine inventor, that was his father. This Charles Parsons ran a tiny engineering firm that barely qualified as a factory. Maybe 20 employees, working in a building that was smaller than most modern supermarkets. They made precision instruments, specialized gears, and custom machinery for clients who needed something that couldn't be mass-produced. Parsons had been reading classified reports about the U-boat campaign because his firm held military contracts, and he'd noticed something that everyone else had missed. The problem wasn't just finding U-boats. The problem was that even when escorts found them, they couldn't catch them. A surfaced U-boat could make 18 knots, faster than most corvettes could manage. By the time an escort worked up to ramming speed or got into depth charge range, the U-boat had often submerged and disappeared into the dark water. What the escorts needed was a sudden burst of speed, not sustained high speed. That required huge engines and massive fuel consumption. Just enough extra power to close the distance in those critical moments when a U-boat was spotted on the surface. 30 seconds of extra speed could mean the difference between a kill and a contact lost. Parsons sketched out a concept that naval engineers told him was impossible. A compact auxiliary engine that could be bolted onto existing escort vessels, providing emergency boost power without requiring major modifications to the ship. It would need to be small enough to fit in spaces that weren't being used, light enough not to affect seaworthiness, powerful enough to add 3 to 4 knots of speed, and simple enough that merchant sailors with minimal training could operate it. Oh, and it needed to be designed, tested, and put into production in less than 6 months, because at current loss rates there wouldn't be a British merchant fleet left by year's end. The Admiralty officers who reviewed Parsons' proposal were skeptical. Auxiliary boost engines weren't a new idea. They'd been tried before on various vessels with mixed results. The engines were usually unreliable, required constant maintenance, and often caused more problems than they solved. Why would this design be any different? Parsons had an answer that changed everything. He wasn't proposing a traditional marine engine. He was adapting aviation technology to maritime use. Specifically, he wanted to use principles from aircraft superchargers to create a compact, high-power engine that could run on the same fuel oil the ship's main engines used. The concept was brilliant in its simplicity. Aircraft engines in 1943 used superchargers to force more air into the cylinders, dramatically increasing power output without increasing engine size. Parsons proposed building a small supercharged diesel engine that would be connected to an auxiliary propeller through a simple shaft coupling. When the crew needed emergency speed, they'd engage the auxiliary engine and the extra propeller would provide the boost. The engine wouldn't run continuously. It was designed for short bursts, maybe 15 to 20 minutes at maximum power before it needed to cool down. But 15 minutes was enough to close on a surfaced U-boat. It was enough to position a ship for a depth charge run. It was enough to make the difference between success and failure in the narrow windows of opportunity that defined anti-submarine warfare. The Admiralty gave Parsons permission to build a prototype, but with zero enthusiasm and a budget that wouldn't have covered a week's worth of destroyer fuel. They basically told him that if he wanted to waste his time and his company's money on a project that probably wouldn't work, they wouldn't stop him. But don't expect government funding, don't expect priority access to materials, and don't expect anyone to take it seriously. Parsons accepted those terms because he understood something the Admiralty didn't. His small factory's lack of size was actually an advantage. Large manufacturers were locked into production contracts, building destroyers, building bombers, building tanks. Their facilities were optimized for mass production of specific designs. Changing those production lines required months of retooling and displaced manufacturing of critical equipment. But Parsons' workshop could pivot in days. His team of 20 skilled machinists and engineers could work on a single prototype without disrupting any major production programs. They could test, fail, modify, and test again with a speed that large manufacturers couldn't match. And because they were small, they were under the radar. No bureaucracy, no competing priorities, no committees arguing about specifications. The team worked with an intensity that bordered on obsession. They knew that every day they spent developing the engine was a day when merchant sailors were dying in the Atlantic. Every hour counted. Every design decision had to balance power, reliability, size, and manufacturability. The first challenge was the engine block itself. Parsons needed something compact but robust enough to handle the stresses of supercharged operation. His team settled on a modified 4-cylinder diesel design, borrowed conceptually from truck engines but engineered to much tighter tolerances. The cylinders were arranged in a square configuration, keeping the engine short and allowing for better cooling. The supercharger was the heart of the system. Parsons adapted designs from aircraft engines but simplified them for maritime use. The supercharger would force air into the combustion chambers at pressures that would have destroyed a standard marine diesel. But the increased air meant they could burn more fuel, which meant more power from the same displacement. Cooling was a nightmare. The engine would be generating enormous heat in a very small space, and unlike aircraft engines that had airflow from forward movement, this engine would be buried in the bowels of a ship with limited ventilation. The team designed an oil cooling system that circulated lubricating oil through passages in the engine block, carrying heat away to external radiators that could be cooled with seawater. The fuel system had to be bulletproof. Parsons knew that merchant sailors and naval ratings weren't going to perform delicate engine maintenance in the middle of a U-boat attack. The fuel injection system needed to work under extreme conditions, ship rolling in heavy seas, engine under maximum load, operators possibly panicking. They designed a mechanical injection system that was so simple it had fewer than a dozen moving parts. And those parts were overbuilt to the point where they could probably survive being hit with a hammer. By August 1943, they had a prototype ready for testing. The engine looked strange. a squat, compact block of metal bristling with pipes, valves, and the distinctive bulge of the supercharger housing. It weighed just 340 pounds, small enough that 4 men could lift it, and when they bolted it to a test stand and fired it up for the first time, it produced 185 horsepower. That might not sound impressive compared to ships' main engines that produce thousands of horsepower, but 185 horsepower from a 340-pound package was an astonishing power-to-weight ratio for 1943. And more importantly, when connected to a properly sized propeller, that 185 horsepower could add 3.4 knots to a corvette's top speed. The Admiralty sent observers to witness the testing, still skeptical but willing to look at results. The engine ran for its designed 15-minute maximum power cycle, cooled down and ran again. It did this repeatedly over a 6-hour testing period without failing. The observers took notes, asked technical questions, and left without making any commitments. 3 days later, Parsons received a phone call that would change everything. The Admiralty wanted to install the engine on HMS Clematis, a Flower-class corvette that was due for a brief refit. If the installation worked and the engine performed at sea, they'd consider a larger trial. If it failed, the project was dead. HMS Clematis was typical of the corvettes that formed the backbone of convoy escort forces. She moved about 950 tons, could make 16 knots on a good day with calm seas, and was designed to be cheap and fast to build rather than comfortable or sophisticated. Her crew of 85 men lived in cramped conditions that were wet, cold, and miserable, even by wartime naval standards. Corvettes rolled abominably in Atlantic swells. They were slow. Their armament was limited, a 4-inch gun, some machine guns, and depth charges. But they were available in numbers that destroyers couldn't match, and they could stay at sea for weeks, shepherding convoys across the killing grounds of the mid-Atlantic where no air cover could reach. Parsons and his lead engineer travelled to the dockyard where Clematis was being refitted. They'd brought the auxiliary engine, carefully crated and accompanied by installation instructions that Parsons had written himself. The dockyard workers looked at the small engine, looked at the corvette's cramped engine room, and expressed serious doubts that this contraption would fit anywhere, much less do anything useful. The installation took 4 days of creative engineering. They mounted the engine low in the hull, just aft of the main engine room, connected to a small auxiliary propeller shaft that extended through a new hull penetration. The fuel lines tapped into the ship's main fuel tanks, the cooling system connected to seawater intakes, and the control mechanism, a simple throttle lever and engine temperature gauge, was installed in the engine room where the chief engineer could reach it. The Clematis's engineering officer, Lieutenant James Mackay, watched the installation with the weary skepticism of a man who'd seen too many wonder weapons fail in practice. He'd been at sea since 1940, had survived 2 ship sinkings, and had developed a profound distrust of anything that promised easy solutions to hard problems. But Mackay was also professional enough to give the system a fair test. Once the installation was complete, he spent 2 days learning the engine's characteristics, how long it took to start, how it responded to throttle inputs, how hot it ran under load, how much fuel it consumed. He ran it repeatedly at dockside, checking for leaks, vibrations, and any sign that it would shake itself apart when the ship was in heavy seas. On September 15, 1943, HMS Clematis put to sea for trials. The auxiliary engine had been warmed up and tested at dock, but now came the real question. Would it work when the ship was rolling, when seawater was spraying over the deck, when everything was cold and wet and miserable? Lieutenant Mackay waited until they were clear of the harbour, then gave the order to engage the auxiliary engine. The chief engineer pulled the engagement lever, advanced the throttle, and the small engine roared to life. The ship's speed, which had been holding steady at 15 knots, began to climb. 15.5 knots, 16 knots, 16.5. The auxiliary engine was pushing the corvette faster than it had ever gone in its operational life. Mackay watched the engine temperature gauge climb toward the red line, counting down the minutes. At the 15-minute mark, he ordered the engine shut down. The chief engineer pulled the throttle back and disengaged the clutch. The Clematis's speed dropped back to its standard cruising pace. They waited 30 minutes for the engine to cool, then ran the test again. Same results. 3 knots of extra speed for 15 minutes, no mechanical failures, no leaks, no problems. The sea trials lasted a week, testing the system in progressively worse conditions. Calm seas, rough seas, following seas, head seas. Every time the auxiliary engine delivered its promised boost, the crew started calling it the afterburner, after the similar systems being developed for jet aircraft. And Lieutenant Mackay, who'd started as a skeptic, wrote a report to the Admiralty that included a line Parsons would frame on his office wall. This device works as advertised and should be installed on every escort in the fleet. But the Admiralty still wasn't convinced. They wanted to see combat results, not just sea trials, and they were about to get exactly that. November 1943 brought some of the worst weather of the war to the North Atlantic. Convoy ONS-20, outbound from Britain to North America, was fighting through storms that sent waves crashing over the escort vessels' bridges. The merchantmen in the convoy, heavily loaded with ballast for the return journey, wallowed through the seas, while their escorts tried to maintain station in conditions that made navigation a nightmare. HMS Clematis was part of the escort group positioned on the convoy's port quarter. The auxiliary engine installation had been kept quiet. The Admiralty didn't want to advertise new technology until they were sure it worked. Most of Clematis's crew knew they had something new in the engine room, but they didn't know what it was supposed to do or when it would be used. On the night of November the 18th, conditions were particularly brutal. Visibility was near zero in driving rain. Seas were running 20 feet or more. The convoy was scattered across miles of ocean, with escorts struggling to maintain contact with their charges. This was exactly the kind of weather U-boats loved because it rendered sonar almost useless and made visual spotting impossible. At 02:30 hours, the starboard lookout on Clematis spotted something that made his blood freeze. A white wake, moving fast, crossing ahead of the convoy. A surfaced U-boat, probably closing to attack position. He hit the alarm bell and shouted the contact bearing. Lieutenant Mackay reached to the bridge within seconds, still pulling on his coat. He grabbed the binoculars and scanned the bearing. There, just barely visible through the rain, a low dark shape with a white wake. Range maybe 2,000 yards and moving fast. The U-boat commander probably hadn't seen Clematis yet, focused on getting into position to attack the merchant ships. Standard procedure was to turn toward the contact and increase to maximum speed, trying to close the range before the U-boat spotted the threat and submerged. But maximum speed for a corvette in these seas was maybe 14 knots, and the U-boat was making at least 16. By the time Clematis could reach the spot where the U-boat had been, it would be gone, submerged and protected by the storm-confused sonar conditions. Mackay made a split-second decision. He ordered the helm hard over towards the contact, then grabbed the voice pipe to the engine room. "Chief, hire the afterburner. Give me everything she's got." Below decks, the chief engineer had been waiting for this moment since the installation. He pulled the engagement lever, felt the auxiliary propeller shaft engage, then pushed the throttle to maximum. The small engine screamed to life, its supercharger howling as it forced air into the cylinders. The corvette surged forward like a horse given spurs. On the bridge, Mackay watched the speed indicator climb past 16 knots, past 17, settling at just over 18 knots. The corvette was shaking with the strain, waves smashing over the bow and sending spray back over the bridge. But they were moving faster than he'd ever felt a Flower-class corvette move, and the range to the U-boat was closing rapidly. The German lookout spotted Clematis at about 2,200 yards, probably alerted by the unusual bow wave the corvette was throwing. The U-boat immediately began an emergency dive, the classic response to an approaching escort. Get underwater, go deep, hope the escort loses contact. But closing 1,200 yards at 18 knots takes less than 2 minutes. The U-boat's conning tower was still visible when Clematis reached attack position. Mackay ordered depth charges dropped in a pattern set to detonate at 150 feet. The corvette raced over the swirl where the U-boat had submerged, and 6 depth charges rolled off the stern. The explosions came seconds later, massive columns of water erupting from the sea. Clematis turned hard to port, preparing for a second run, but it wasn't necessary. Oil bubbled to the surface, followed by debris. The U-boat had been caught during its dive, when it was most vulnerable, and the depth charges had crushed it. The entire engagement, from first sighting to kill, had lasted less than 5 minutes, and it only worked because the auxiliary engine had given Clematis the extra speed needed to close the range before the U-boat escaped. Without that boost, the submarine would have submerged cleanly and disappeared into the storm. The report Mackay filed after returning to port was explicit. The auxiliary engine had enabled a kill that would have been impossible with standard corvette performance. The Admiralty's remaining skepticism evaporated. They wanted the engine installed on every escort vessel that could accommodate it, and they wanted production ramped up immediately, which presented Parsons with a completely different problem. His small workshop could build prototype engines and even small production runs, but the Admiralty was talking about hundreds, possibly thousands of installations. His 20 employees couldn't possibly meet that demand. The solution required the same creative thinking that had produced the engine in the first place. Instead of trying to scale up his own factory, Parsons designed the engine to be manufactured in pieces by multiple small workshops, then assembled at central locations. The engine block could be cast at one facility, the supercharger built at another, the fuel system at a third. Each component was standardized and simple enough that small engineering firms could produce them without specialized equipment. This distributed manufacturing approach meant that losing any single facility to German bombing wouldn't cripple production. It also meant that small workshops across Britain that had spare capacity could contribute to the war effort without disrupting their main production. A machine shop that made tractor parts could produce auxiliary engine components without retooling their entire facility. By January 1944, production had ramped up to 20 engines per month. By March, that number had doubled. Small workshops in Manchester, Birmingham, Glasgow, and a dozen other cities were producing components. Assembly facilities in Liverpool and Portsmouth were putting engines together and shipping them to dockyards for installation. The installation process had been refined and simplified. A skilled dockyard team could install an auxiliary engine in a corvette or frigate in about 3 days, compared to the 4 days required for the prototype installation. Ships that came in for routine maintenance would leave with the auxiliary engine installed as a matter of course. The impact on convoy battles was immediate and measurable. Escorts with auxiliary engines were achieving U-boat kills at rates significantly higher than vessels without them. The extra speed wasn't just useful for closing on surfaced submarines, it also improved the escort's ability to reach threatened parts of the convoy quickly, to pursue sonar contacts before they faded, and to maintain station in heavy seas. German U-boat commanders began reporting in their war diaries that British escorts seemed faster than before. Intelligence analysts in Berlin initially dismissed these reports as combat stress or exaggeration. But as more and more U-boat commanders made similar observations, German naval intelligence began to suspect that the British had developed a new class of escort vessel. This misunderstanding was exactly what the British wanted. The Admiralty had classified the auxiliary engine program at the highest level. Captured U-boat crews were interrogated carefully to see if they knew anything about British escort capabilities, but the Germans seemed to think they were facing new ships rather than modifications to existing vessels. The disappointment was so successful that German intelligence devoted resources to tracking new British escort classes that didn't exist. The Battle of the Atlantic reached its turning point in May 1943, before the auxiliary engines were widely deployed. That month, U-boat losses spiked dramatically due to a combination of improved radar, escort carriers providing air cover in the mid-Atlantic gap, and better tactics. Admiral Dönitz temporarily withdrew his submarines from the North Atlantic, conceding that convoy battles had become too costly. But when U-boats returned to the offensive in the fall of 1943, they found that British escorts had become even more dangerous. The auxiliary engines were one part of a comprehensive improvement in Allied anti-submarine capabilities. Better sonar, better radar, better weapons, better tactics, and now better speed when it matters most. The statistical impact is harder to isolate than something like radar or sonar because the auxiliary engines didn't find U-boats, they just helped escorts reach them faster. But analysis of convoy battles from late 1943 through 1944 shows a clear pattern. Escorts equipped with auxiliary engines achieved contact-to-kill conversions at rates about 25% higher than escorts without them. That might not sound dramatic, but in the context of the Battle of the Atlantic, it was enormous. If an escort group had even a 25% better chance of killing a U-boat that had been detected, that meant fewer torpedoes fired at merchant ships, fewer losses, and more critical supplies reaching Britain. By mid-1944, over 400 escort vessels had been fitted with Parsons auxiliary engines. Production had reached 60 engines per month, and the system was being adapted for installation on larger vessels, including destroyers and frigates. The original corvette installation had proven so successful that naval architects were designing the next generation of escort vessels with built-in auxiliary boost systems rather than retrofits. Charles Parsons received an OBE for his contribution to the war effort, though the citation was deliberately vague about what exactly he'd done. The auxiliary engine program remained classified long after the war ended, partly because the Royal Navy continued using the systems on post-war vessels, and partly because the Admiralty didn't want to advertise how effective such a simple modification had been. The irony wasn't lost on Parsons. His tiny factory, operating out of a building that was barely larger than a warehouse, had produced a weapon system that was installed on hundreds of ships and contributed to winning the Battle of the Atlantic. Meanwhile, massive shipyards were building entire escort vessels that took months to complete and required thousands of workers. There's a lesson in that disparity. Sometimes the most important innovations don't come from the biggest programs or the most expensive development efforts. Sometimes they come from small teams working with limited resources, focused on solving one specific problem exceptionally well. The auxiliary engine wasn't elegant, it wasn't sophisticated, it didn't represent a revolutionary breakthrough in marine engineering. It was a clever adaptation of existing technology, executed by skilled craftsmen, designed to do exactly one job in exactly the circumstances where it would matter most. And it worked. In the cold mathematics of naval warfare, where success is measured in ships saved and tonnages delivered, the auxiliary engine program achieved results that were out of all proportion to its size and cost. The Battle of the Atlantic officially ended in May 1945 with Germany's surrender, though by that point U-boat operations had been reduced to desperation attacks that achieved little. The convoys kept running, the supplies kept flowing, and Britain never faced the starvation blockade that had been Germany's goal. Thousands of factors contributed to that victory. Code breaking at Bletchley Park, long-range patrol aircraft, escort careers, improved depth charges, better training, superior logistics, the entry of the United States into the war bringing unlimited industrial capacity. Each element was critical, and removing any one of them might have changed the outcome. But buried in that list of critical factors, rarely mentioned in histories of the battle, was a small diesel engine built by a tiny factory in Letchworth Garden City. An engine that gave convoy escorts just a little more speed at the moment they needed it most. A few extra knots for a few critical minutes, repeated hundreds of times across 3 years of warfare. The merchant sailors who survived torpedo attacks never knew why their escorts suddenly seemed faster. The U-boat crews who died when their submarines were caught during emergency dives never knew what had changed. The vast majority of people involved in the Battle of the Atlantic never heard of Parsons' auxiliary engine, but the convoys made it through, the supplies reached Britain, and a small factory's contribution to that victory was as real as any battleship or bomber. Post-war analysis of the Battle of the Atlantic identified several key turning points: the breaking of German naval codes, the closing of the mid-Atlantic air gap with escort carriers and long-range patrol aircraft, the introduction of improved sonar and radar, the deployment of anti-submarine hunter-killer groups. Each of these developments reduced U-boat effectiveness and increased Allied success rates. The auxiliary engine program doesn't appear in most histories because it was classified for decades, and even after declassification, it seemed too minor to warrant attention compared to major weapon systems. But the people who knew, the convoy commodores, the escort group commanders, the captains who'd fought through 1942 and 1943 with obsolete corvettes, they understood what those few extra knots meant. Captain Donald McIntyre, one of the most successful U-boat hunters of the war, wrote in his memoirs about technical improvements that had helped win the battle. He mentioned radar and sonar prominently, but he also included a brief paragraph about auxiliary power systems that gave escorts improved response times. He couldn't be more specific due to classification, but he noted that the improvement in kill rates after these systems were deployed was statistically significant and operationally invaluable. The engine design itself became the basis for post-war emergency power systems on various vessel classes. The principles Parsons had pioneered, compact, high-power density engines for auxiliary use, influenced marine engineering for decades. Modern ships use auxiliary engines for completely different purposes, but the underlying concept of having emergency boost power available traces back to that small factory in 1943. Perhaps the most telling testament to the program's success was its expansion beyond convoy escorts. By 1944, auxiliary engines were being installed on minesweepers, where the extra speed helped vessels clear dangerous areas faster. Landing craft used modified versions to improve beach approach speeds. Even some submarines received auxiliary systems to improve surface speed when charging batteries. The final production run of Parsons' original design came in 1946, after the war had ended, but while the Navy was still converting wartime vessels to peacetime roles. The total production reached approximately 1,200 engines, installed on over 600 vessels. Not every installation was directly responsible for a U-boat kill, but every installation improved the odds for the escorts and the convoys they protected. Charles Parsons returned his factory to civilian production after the war, building precision instruments and custom machinery as he had before 1939. He never sought publicity for his wartime work, gave few interviews, and declined offers to write about the auxiliary engine program. When he died in 1958, his obituary mentioned his wartime contributions only in passing, noting that he had developed engineering solutions for naval vessels. The workshop in Letchworth Garden City, where the first prototype was built, was demolished in the 1970s to make way for a shopping centre. There's no plaque, no memorial, nothing to indicate that one of the war's more successful weapon systems was developed in that location. Most people who shop there have no idea that 70 years ago, 20 engineers and machinists worked 80-hour weeks in that spot, racing against time to build an engine that would help save their nation. That's perhaps fitting. The auxiliary engine program was never about glory or recognition. It was about solving a specific problem with limited resources in minimal time. It succeeded because it focused on doing one thing exceptionally well, rather than trying to be a comprehensive solution to all convoy defense challenges. The Germans mocked British technology throughout the war, convinced of their own superiority. They built larger U-boats, faster U-boats, U-boats with better sensors and weapons. They developed acoustic torpedoes, snorkel systems, and streamlined hull designs. Each innovation gave them temporary advantages that the Allies had to counter. But they never figured out why British escorts suddenly seemed faster in late 1943. German intelligence never identified the auxiliary engine program. Post-war interrogations of German naval officers revealed that they'd assumed Britain had simply built a new class of escort vessels with more powerful main engines. The idea that the British had retrofitted existing ships with small auxiliary engines never occurred to them. That intelligence failure was strategic. Resources spent trying to counter a new escort class were wasted. German naval architects designed U-boat improvements to counter threats that didn't exist, and the real source of the British advantage remained undetected and uncompromised throughout the war. In the final accounting, Britain's smallest factory didn't win the Battle of the Atlantic alone. No single weapon system or technology could claim sole credit for that victory. But in the complex equation of convoy defense, where dozens of factors determined whether merchant ships lived or died, Parsons' auxiliary engine was a significant term. It gave escorts the speed they needed when they needed it most. It allowed corvettes to catch U-boats they couldn't have reached before. It saved convoys, saved ships, saved lives. And it did all of this while being built by 20 people in a workshop that wouldn't qualify as a factory by modern standards. That's the real story, not the triumph of industrial might or technological sophistication, but the victory of focused innovation. A small team, a simple idea, executed brilliantly under pressure. The kind of victory that rarely makes headlines, but changes the outcome of wars. The auxiliary engine Charles Parsons designed in 1943 wasn't the most powerful weapon Britain deployed in World War II. It wasn't the most advanced, the most expensive, or the most celebrated. But it was exactly what was needed, when it was needed, built by people who understood that perfect is the enemy of good enough. And in the cold waters of the North Atlantic, where merchant sailors died in oil fires and U-boat crews were crushed in their steel coffins, good enough was sufficient to tip the balance. Good enough was victory. The auxiliary engine program remained classified for decades because the best victories are often the quietest ones. This channel uncovers those hidden stories, the small factories, the forgotten heroes, the simple ideas that changed everything. Subscribe to join me in bringing them to light. More untold history is coming.